Let's do some more problems involving phase diagrams. We want to draw a TV diagram, a PV diagram, and a PT diagram for several different phases. So we've got water at 3 different states. All the states are at the same temperature of 300 degrees Fahrenheit, but state A has a pressure of 20 psi, state B has a pressure of 90 psi, and for state C, we don't have a pressure, but the specific volume is given as 5 cubic feet per pound mass. And we want to determine the phase of each of these states, and we want to plot them all on a TV diagram, a PV diagram, and a PT diagram. All right. Now, all of them are at 300 degrees Fahrenheit, so all are going to lie on the same horizontal 300 degree Fahrenheit line that is on a TV diagram. So let's start with the TV diagram. They're our most common diagram. So we have temperature versus specific volume. We have a vapor dome. Okay, and we know at 300 degrees Fahrenheit, which is this horizontal line here, we can look in the saturation table. Now this is the English version of the saturation table, and it's organized by temperature. So I'm going to come down here to 300 degrees, and I see that the saturation pressure is 66.98 psi. So let's lay in that pressure line. We've got our 300 degree temperature line, and we know the 66.98 psi pressure line is going to lay right in on top of it. So this 66.98 psi line goes up to the right, goes under the vapor dome, lying on top of the 300 degree Fahrenheit line, and then up to the right again. Now we also had pressures of 20 and 90 psi. Well, I can lay those in because 90 psi is above 66.98 and 20 psi is below 66.98. So I'm going to go ahead and draw in this 20 psi line and this 90 psi pressure line. So where do these states lie? Well, we'll look at the, for this saturated mixture state at 66.98 psi, we can look up the specific volume in the table here. It's given as 0.01745. And the value of the saturated vapor specific volume is given as 6.472. So we have those points. And we can see that for state C, where we have a specific volume of 5 cubic feet per pound mass, that 5 lies between V sub F and V sub G. So we know state C is a saturated mixture located in this area of the area under the vapor dome. So C will be plotted there. Well, what about state A? At 300 degrees Fahrenheit and 20 psi, state A will exist where this 300 degree Fahrenheit line crosses the 20 psi line. So state A is going to be right here. And state B is 300 degrees Fahrenheit and 90 psi. So it will exist where the 90 psi line crosses the 300 degree Fahrenheit line. So that's where state B lies. And we got all this data from the saturation curve at 300 degrees Fahrenheit. Now that we know the phases of each of the 3 states, it's easy to plot a PV diagram. So here we have a pressure versus specific volume diagram, have a vapor dome, and a constant temperature line on a PV diagram goes down to the right, but it's always horizontal under the vapor dome. So we'll call this our 300 degree Fahrenheit constant temperature line. Okay. And then we can put our pressures in. We know that at 300 degrees Fahrenheit, the saturation pressure is 66.98 psi. So we can put that right here. 20 psi is below that, and 90 psi is above that. State A is where our 20 psi line crosses the 300 degree Fahrenheit line. State B is where the 90 psi pressure line crosses the 300 degree Fahrenheit line. And we already knew prior that state C was a saturated mixture at 5 cubic feet per pound mass, which lies between V sub F and V sub G. So it's a saturated mixture right here. Now let's plot a pressure temperature diagram, which looks very different. It doesn't have a vapor dome. Okay. We have a line here that separates solids from vapors. We have a line here that separates solids from liquids. We have a line here that separates liquids from vapor. And that line ends abruptly at the critical point. All right. So as a reference, let's note that the critical point temperature is 705.4 degrees Fahrenheit, and the critical point pressure is 3204 psi. Now our states A, B, and C lie at 20, 66.98, and 90 psi, which is below 3204. Okay, and I know that state A is, well, let's look at it this way. All of these states, A, B, and C, lie at 300 degrees Fahrenheit, which is a vertical line. Okay, and this 300 is less than 705. So it's going to cross this line between the triple point and the critical point. And we know that A was at 20 psi and that it was a superheated vapor. So it's going to be here. We know that B was at 90 psi and that it was a subcooled liquid, so it's going to be up here. And we know that C was a saturated mixture at 66.98 psi. It's going to be right on top of this line between the triple point and the critical point. And so that gives us our PT diagram. Now there's some other interesting things about this diagram that I want to show you. Vapor and gas are often used interchangeably. And in this class, I don't care if you call something a vapor or a gas, but there is a difference. We tend to call a gaseous version of water, we don't call it water gas, we call it water vapor. And when we refer to the air around us, we don't call the air a vapor, we call it a gas. Well, why is that? Here's the rule. If I have a state and it's a vapor, like state A here, if I increase the pressure at constant temperature, which means I'd be going straight up, and if it becomes a liquid, it is defined as a vapor. And so any vapor, so if I have a gaseous state below the temperature of the critical point, then we will call it a vapor, because when I increase its pressure at constant temperature, it becomes a liquid. Now, if this gaseous state is above the temperature of the critical point, you can see that if I hold its temperature constant and increase its pressure, because it's to the right of the critical point, it never becomes a liquid. And so we'll call a gaseous state that's above the critical point temperature, but below the critical point pressure, we'll call that a gas. And finally, we have the region that is both above the critical pressure and the critical temperature. And it turns out that that is neither a liquid nor a gas, because liquids and vapors can no longer be distinguished in the region above the critical point. And so we simply call them supercritical fluids. So really there are three different names for this state. We have vapor, we have gas, and the supercritical fluid is really, like I said, it's not a gas and it's not a liquid. We just call it a supercritical fluid. So I thought that you would find that interesting.